Next, let's consider the case when gravity is doing work. So imagine we have a book that is dropped from a higher position to a lower position. Gravity is doing work as the book changes its position, and the amount of work done by gravity is equal to the amount of the gravitational force times the amount of displacement times the cosine of the angle between those two vectors. In this case, we can see that the direction of the gravitational force and the direction of the displacement is both downward. They're in the same direction, so the cosine of theta would be equal to 1, since the angle between those two vectors is 0. So the work done by gravity in this case would be mg times the initial position minus the final position. Now you may think, wait a minute, I thought delta y was always final minus initial. But remember, we're finding the amount of displacement, which is a positive quantity, and since the initial position is higher than the final position, we need to take the initial minus the final in order to get a positive quantity for the displacement. So this amount of work can be rewritten by multiplying mg over the parentheses by mgy initial minus mgy final. Now we call this quantity the mass times gravity times the height of the object or the position of the object. We call that the gravitational potential energy. So the gravitational potential energy for an object near the surface of the Earth is defined as being mgy. And we can also see that the work that's done by gravity is equal to the negative of the change in the gravitational potential energy. Since this change in gravitational potential energy is equal to work, gravitational potential energy has the same units as work, which is to say that its units are joules. Now, one question we might ask is, when is the gravitational potential energy equal to 0? Well, if we've defined gravitational potential energy to be mgy, then if the gravitational potential energy is 0, then that must mean that the position is 0. Y is equal to 0. But we know that where y is equal to 0, that's going to depend on our choice of coordinate system. Often we choose y equals 0 to be ground level, but not always. The most important thing is to choose that y equals 0 location so that it's the most convenient for your problem, and then be consistent when you're looking at different parts of that problem. So if we are in a situation where the only force acting on an object is gravity, and if gravity is the only force that does work, then we can say that the net work is the work done by gravity, which is minus the change in the potential energy. But we also know that the net work is equal to the change in kinetic energy, or the final minus initial kinetic energy. So rewriting this, we can say that the initial minus the final gravitational potential energy is equal to the final minus initial kinetic energy. Now, if we take this equation and rearrange it so all of the initial quantities are on one side and all of the final quantities are on the other side, we can see that the initial sum of energy is equal to the final sum of energy. So we say that this sum of energies is equal to the total energy, and that the total energy is conserved. Now, if we want to write this out in a form that's most convenient for solving problems, we would say that the initial potential energy, mgy initial, plus the initial kinetic energy of an object, 1/2 mv initial squared, is equal to the final potential energy plus the final kinetic energy. So here you can see a couple of animations showing you conservation of energy for a pendulum. In this first animation, the one on the left, you can see a pendulum swinging back and forth. And as well, you can see some meters which are showing the gravitational potential energy and the kinetic energy of the pendulum as it moves. So you'll see that the kinetic energy, as you might expect, is minimum. It drops to 0 when the pendulum stops moving at the top of the swing. So at the top of the swing on either side, the velocity of the pendulum temporarily drops to 0, and that's when the kinetic energy of the pendulum drops to 0. In the middle of the swing, down here at the bottom, that's when the pendulum is moving the most quickly and so has the most kinetic energy. On the other hand, the gravitational potential energy is biggest when the y position, the height of the pendulum, is the biggest on either end of the swing, and it drops to 0 if we define the lowest part of the swing to be our y equals 0 location. So you can see that the total amount of energy is conserved. The energy goes from being gravitational potential energy to kinetic energy and back and forth over and over again as the pendulum is swinging, but the total amount of energy remains the same. So in this other demonstration, you have kind of a classic demonstration where a bowling ball is attached by a cable to the ceiling. So here we have Neil deGrasse Tyson, who lets the bowling ball go. The bowling ball swings out, comes back, and boops him in the nose. And he knows that it's only going to be a gentle boop and not a smash because the total amount of energy of this pendulum is conserved. If he holds it in an initial position and lets it go, it will not gain any additional energy when it swings back and hit him in the face hard. It will come back to the same height at which he released it and stop because the total energy of that pendulum is conserved. So here is a question for you. Let's say you have 3 identical balls thrown off a building with the same speed. You throw ball 1 at an angle of 40 degrees above the horizontal, ball 2 is thrown directly horizontally, and ball 3 is thrown 40 degrees below the horizontal. Rank the speeds of the 3 balls when they reach the ground.